Good morning, everyone. This is Jim Chastain with EasyPower, our Tuesday morning refresher session. Welcome everyone to the discussion. Today's topic is mitigation techniques for arc flash incident energy. And let me say at the outset that this is not a list of recommendations or even suggestions. The focus for this session is to how to utilize the EasyPower tools and considerations of different alternatives that you may have for your specific system. So with that, welcome. And let me start with this poll. How often do your projects require mitigation? Or you feel the need to do mitigation? Just want to get some feedback, in part to maybe modify where some of my time is spent during this discussion, but certainly I appreciate your participation. And so here's kind of how the group is stacking up. And then the second question is, most often when you do require mitigation, are you looking at new buildings, old buildings, or new construction? And this you will see as we get into the discussion. This is a significant factor in terms of what your options are, the cost of the options, and as kind of an amplification of the value that I'm going to be speaking to, and you'll see how we utilize the tools to compare these different options. So it looks like we're kind of heavily leaning towards, and this is frankly the reality of the real world, and that is the reason there is such a push on arc flash from government and regulatory bodies is a lack of understanding in older facilities that that was a very dangerous situation. So appreciate the feedback. So what our agenda today is if we're going to be talking about mitigation, that basically suggests that we already understand and have analyzed the system's physical construction and the electrical properties, and we've optimized the performance of the system's elements. So this is where the EasyPower tools bring exceptional value in modeling the system, and based on those results, we face a decision about what to do on any unsafe conditions, which could be a potential source of harm either for personnel or for vital equipment. So those choices fall into three distinct categories. The potential solutions vary widely, especially if you have the possibility of addressing them during facility construction, and your options are not nearly as limited as compared to what you have to do with an existing facility. Again, the EasyPower tools allow a significant amount of insight even during a review cycle of a new building design cycle, so that some of these decision points can be addressed early on. So for most of the balance of this session, I'm referring primarily to the options for existing facilities where complete change out of a switchgear components may be prohibitive. So bear in mind, this is not a list of recommendations, and I don't want to beat that one into the ground. I think it's important to note at this point that for several years now, NFPA has made a distinction between hazard and risk when it comes to arc flash. Conducting an arc flash study will reveal parts of the system that may represent high levels of incident energy, which might be harmful to personnel or equipment. But as such, the study will present the description of the hazards in the system, but the study itself does not preclude or prevent an arc flash. In other words, doing a study doesn't prevent the arc flash event. The purpose of the study is to analyze the worst possible case and determine, one, would the system survive that event and the equipment work properly, and two, factor these worst case events into what your particular situation or operations requirements are. And that brings up the discussion about risk. Risk, on the other hand, according to NFPA 70E, is an amalgam of several parameters including severity of harm or probability of occurrence of harm, the frequency and duration of exposure, and this is all combined into a weighted factor that NFPA refers to as the risk valuation. Now, according to the NFPA 70E, there are 5 basic areas to consider for safety improvement. The most effective results will occur when all 5 areas are taken into account with a holistic approach. So most of what falls into the engineering controls category, since these are the methods to reduce the incident energy itself. But please don't overlook or underestimate the benefits of maintenance, improvement in procedures, and above all, improvement in training of personnel. Maintenance, because it will help prevent degraded equipment performance, and training, which can reduce the amount of human error as a source of arc initiation. And again, some of these details will be a combination of multiple categories. Okay, so first of all, I want to talk about how physical dimension and location factor into calculating incident energy. The energy is radiated in a 360-degree basis, and the energy density decreases with the square of the distance from the energy source, or the arc itself. It also, if you're looking at a closed box and the operator is standing at the only opening to that box, there is an amplification effect because of the reflection of energy into or through that opening. And so understanding this may be a way of mitigating some of the danger or some of the harm that could occur in a worst case condition. So in this first picture, the equipment is properly installed and maintained, covers are closed and secure, and there's no evidence of malfunction. So to operate the circuit breaker, NFPA doesn't require PPE in this particular case. But from the incident energy calculated on the panel behind the cover, we know significant energy is present to cause harm. So because an operator or some number of these breakers needs to be operated during live energization or live work, we have written a procedure up, or the company has written a procedure up, or the operator who's going to operate one of these circuit breakers wears extra protection over his hearing in this case, and the arm that's going to operate the circuit breaker, and the instructions are to stand to the right and behind the opening of this particular panel before he operates the breaker. Consequently, we haven't done anything to mitigate the energy, but we've done a significant amount to mitigate the potential harm to an individual. And frankly, this is frequently the case in an older facility. Now, the second procedure, the second picture here, is an example where we have the ability to put the operator at a farther distance, safer distance, and rather than work with an 18-inch working boundary or working distance, we've extended that, and thereby permitting a lower calorie rating for the operator when he's going to do this particular operation. So let me jump out of this, and I'm going to show you where this shows up in EasyPower. And when we calculate incident energy in EasyPower, for instance, this bus, you'll notice as we fault the buses and calculate incident energy, this is a fairly significant level. And if I require this, some operators or technicians to work on this bus while it's energized, this is a significant level of PPE that's required. Well, how this has been calculated, again, it's important to understand the system. In the arc flash hazard controls, first of all, you can see that we're using a working distance here of calculating 18, 24, and 36 inches. And if I have a concern, because this is calculated at 18 inches, and I have the ability to move the operator back for this particular operation, the question is, how much can I reduce the PPE requirement? The way EasyPower presents this is when I look at the incident energy arc flash hazard report, I can see that my main is a 480 volt bus. It's protected by the fuse upstream. It has a bolted fault current and a arcing current of 10,000 amps, and at a working distance of 18 inches we're seeing 16.1 calories. At 24 inches it's 10.5 calories, and at 36 it's 5.8 calories. So if we have a way to extend the operator while he has to work on this bus or operate this equipment while it's exposed as much as 36 inches away, I can reduce the PPE required. Again, I haven't changed the actual incident energy at the bus, but I've considerably made safer or more safe the conditions of the operation that we just described. All right. Along the same lines is the potential to put up a physical barrier. Now again, what we're looking at here is a temporary situation where we need someone to work on the hot equipment in closer contact, and if we look at the conditions of the bus, we end up with significant danger and potentially the need to wear PPE that would make the working conditions intolerable or limit the dexterity and potentially even make the tasks more dangerous. So one of the I don't want to say tricks, but one of the techniques that most electricians are familiar with is putting up a temporary barrier to prevent inadvertent contact with electrified buses at 480 volts, for instance. In this particular case, they've used a clear drape. In this case up here, they have a rubberized drape that you can't see through, and so this is a fairly common technique. In arc flash considerations, probably the most dangerous situation occurs when you remove the panel and inadvertently touch, drop, fall, or cause the panel itself to touch an electrified bus. So what I'm describing here as far as a temporary barrier may best installed as a under de-electrified or de-energized conditions, set the barrier up. And the reason to do this, again, when we go back to EasyPower and we look at the short circuit options that are being used for these calculations, you'll notice in the case of this main bus, we've been required to exclude the main breaker's capabilities. The reason for that was exactly the picture we're looking at, where as we open up the panel, we're exposed to the top side or upper connections to the protective device. So consequently, because an arc could jump across that breaker, we can't use the protective parameters that the breaker affords us. EasyPower lets us look at the possibilities like, well, what would happen if we were able to set a barrier up, albeit temporary? Can we utilize that breaker then for protection of people working on the bus? And the answer appears to be yes, that if we were able to utilize that breaker, it would bring the PPE requirements down to a very civil level. And again, this gives us a lot of possibilities when it comes to a temporary working condition. So again, it's one alternative to work on a temporary basis if I need to work on this bus hot. Another alternative, again, better understanding my system, is to make some adjustments to any type of adjustable devices we have, because whether we like it or not, there's always a potential that the as-read values could be adjusted or could be even temporarily maladjusted when we did our study. So let's kind of look at this alternative. I guess I want to talk about fuses first. The point that I'm going to go to here is all fuses are not the same, and just selecting a 400 amp fuse doesn't necessarily give us the same protection in every case. So let's see what this means in EasyPower, or what EasyPower helps with this. So let's compare several different fuses, everything from the same manufacturer, same rating, but they're different styles. And the way we want to look at the trip characteristics or the protection curves is in the coordination module, not the power flow. The coordination module, I'm going to highlight all the devices and plot the curves, and then let's fault each of the panels. And as we fault this panel and show the incident energy, you can see that this fuse gives this panel a arc flash boundary of 7 inches. And again, it's because this is a relatively steep, relatively lower curve or more protective curve for that fuse, for that circuit. We have the exact same fault current in every case. So let me kind of illustrate that. We have just under 8,000 amps of bolted fault current in every case. And so as we fault each of the individual buses and look at the incident energy, you can see that this center panel has a very high incident energy compared to the other two. If we look at its current alone, or trip characteristics alone, we can see that its curve sets to the right. And when I look at the arcing current, you can see that we're actually having to utilize, for the calculation purposes, the 85% point. IEEE requires that we compare 85% with 100% arcing current to find the most restrictive incident energy. So in this case, we're seeing a tripping point of this fuse almost at 300 milliseconds, and consequently the arc, if it were to be initiated, would last longer at this panel than it would at the other two. So again, consider alternatives in terms of different types of fuses, even if you can't reduce the size or improve the speed of the tripping of the type of fuse you're using. The next alternative, again, is the one I was kind of jumping ahead to, and that is consider exactly what's going on with your adjustable breakers. Probably one of the more difficult coordination issues is molded case circuit breakers, and so EasyPower can show us what our alternatives are there when we're talking about molded case. So let's go back to our situation where we have an incident energy calculated, and we have a particularly high incident energy here when it's actually lower up above. So the question is this real? And the way we determine that is we look at the arc flash hazard report. Let's just fault the single bus. We're showing that it's a 480 volt bus. It's protected by BL2, which is the breaker that we're concerned about. We have actual arc, the worst case arcing current during a fault would be 4,800 amps. That is a significant fault, but according to the breaker manufacturers, it's taking 9 seconds to trip this particular device. So while this is a real calculation, this may not be necessarily real or necessary in terms of the settings on the breaker. So again, as we go back to coordination focus and look at the trip points, what the tool shows us, so these are TC curves, and what we're looking at is, in this case, the thin blue line is a starting curve for the motor. So this is, any protective device needs to be set up with its curve to the right of this thin blue line. This teal colored curve are actually the trip characteristics of this particular GE circuit breaker, and what we're seeing if we fault this bus is bolted fault current of 7,723 amps, and I can put in the arcing current, and as we look at this, again, we're using the 85% value of the arcing current because it's most restrictive. Molded case circuit breakers are by design have a particularly steep drop-off here as far as their performance, and the manufacturer doesn't guarantee the breaker to clear until we get to the right-hand side of this curve. So in terms of arc flash calculations, this is what the IEEE model requires us to use, which ends up being the 7-second, or excuse me, the 9-second number that we saw in the chart. How do we adjust that? Well, with this, the problem is we have a long extension or a long run, consequently lower arcing current, and it may be useful for us to, as we kind of hover over this curve, be able to adjust a different trip setting to a little bit lower. And as we do that, we notice now that our curve falls, our current falls on the lower part of this curve, and consequently, without making any changes to the system other than a slight adjustment to the trip settings for this breaker, we have a much more civil situation in terms of working on this particular bus hot. Okay, and again, that's a fairly common situation when we're using multi-decay circuit breakers. All right, and most of these are, again, procedural or adjustments with current devices on multi-decay circuit breakers or fuses. Okay, when we get into active mitigation, the first, at least on my list, is a process called zone selective interlocking. And this involves, the object is to trip the breaker closest to the fault without time constraints and still maintain system coordination. And this is accomplished by a communications link between the feeder breaker and the main breaker or relay. And what it allows the system to do is, if there is a fault detected, there's a communications between the feeder breaker and the main delays and allows the breaker closer to the fault to trip first. If a fault occurs and there's not this communication links, and in fact, what it means is the main breaker says, hey, no one else is telling me they see this fault, then the main breaker will trip on its original settings. Again, which will give us better coordination and better protection along the way. So let's see an example of that. And again, this is not necessarily endorsing any particular manufacturer. It's just showing how these techniques work and how they're modeled. So we're going to go into short circuit focus, and as we fault it, and again, this is easier to see if I'm in coordination focus. As I fault this bus and see what the incident energy is, I'm in a mode where these particular breakers have zone selective interlocking set to on. And what that means is, if this breaker, let's plot it while we're there. So what we're going to plot are the TC curves for these two breakers. And you can see before there's a fault, both breakers are set to be able to trip relatively fast. When the downstream breaker trips or recognizes a fault, the upstream breaker puts an intentional delay in, permitting the downstream breaker to do its thing and still provide a backup coordination if for some reason it doesn't clear in a certain amount of time. On the other hand, if a fault occurs that doesn't include this communications, then the main breaker will trip in its original set points, and we get protection on both fronts. So that's referred to as zone selective interlocking, and it's a system that's built into. It's a matter of adding some equipment, providing this communications link between the main breaker and the feeder breakers downstream. So there is some advantage, and it uses standard parts, and it's a matter of adding some communications link between existing elements. Again, you may have some problems with coordination of the main because it may require that you have higher incident energy due to breaker speed limitations. Another similar protective scheme is called maintenance mode. Again, here there's a communications link that we can invoke by electrical signal or by manual button, but it lowers for a temporary period of time the protection delays on relays or devices upstream and allows us to work on downstream systems in a more safe condition. It's temporary because the setup may not allow normal transitions in motor starting or load coming online, because the spike may be interpreted as a fault. So let's see how that shows up. So again, this is called maintenance mode, and it's a feature that's built into many molded case circuit breakers, many low power voltage circuit breakers that are adjustable by invoking maintenance mode. So let's go ahead and short the circuit, look at our incident energies. You can see that we have fairly high incident energies during normal operations. If I now invoke maintenance mode, set everything to on, then these upstream breakers are set with a more sensitive setting and allows us to work on the downstream buses in a more safe condition. And again, if we look at this same effect in the TC realm, when we turn maintenance mode on, all the upstream the delays in all the upstream devices is minimized or set to minimal points. If we turn it off for normal operations, you can see there's a delay on all the upstream devices, and consequently we have coordination and we can withstand transitions in the system, load transitions. So the next level of elevated protection in this overall scheme is something we refer to as differential relays. And again, the relays are, it works in conjunction with normal phase protection, but the situation is that we have a relay that can compare the incoming current versus the outgoing current and determine whether there's an imbalance that can be considered to be a fault. EasyPower tools will let us look at that, and before I go there, just to save some time, it's the same setup as the technique used to model arc flash relays. So arc flash relays are a newer technology that are activated by a network of fiber optic light sensors. The theory is, or the fact is, that as they determine a bright flash, then they generate electrical signal to trip upstream devices. Very quick response, but they can be limited. In fact, in both of these cases, the limitation could be the opening time of the breaker itself. So let me kind of close some of this stuff and we'll open up that example. Again, these are tools that are available in EasyPower, and it's just a matter of modeling them in the accurate way. All right, so here we have several relays that are protecting phase currents, and then one relay that's protecting or comparing the input current to all three loads. And if we have a fault in EasyPower, I guess I need to go to short circuit focus and fault the bus, what we see in our results file is that the main switchgear faulted on a normal phase over current. So the question is, what's going to happen if we have and you'll see we have fairly high incident energy at any one of these buses. So can we improve that with a differential relay? The way we would improve that is go to our bus that's being protected, go to the arc flash hazard report, and in this case go to user-defined times. The device that we want to signal is going to be the differential mode of the relay, which is, so we're going to set this up as a differential relay, and the response time according to the manufacturer Could be as quick as a tenth of a second or as slow as 150 milliseconds. So let's say for right now we have the ability to simulate using 110 milliseconds. So let's go back to short circuit focus. Fault this bus. And now we see from our arc flash hazard report that we're having a differential fault, and our incident energy is much more reserved because of the ability for this relay to operate much quicker. And so again, it would apply if this, because we're going to be opening up the main high voltage breaker, it would protect all the system if we determined, or if the relay could detect the imbalance between any of these relays. Same thing happens, the same theory happens if this were an arc flash relay as opposed to a differential relay. Whatever location the sensor was in, and it could be in all of the panels or all of the key critical panels, that it would respond by shutting the system down, disabling or opening the main breaker or whichever breaker we have the signal going to, and have a predictable response time that could then be modeled in EasyPower, and we can see what our results would be. And then the last on my list is a newer product that's referred to as a relay controlled fuse. And in effect, because fuses are relatively more cost effective, what this scheme requires is a sensitive relay that can be placed on the downstream side, the load side of my system. And during normal operations, the current is channeled through the main fuse, through the bypass switch for normal operations. But as soon as a fault were detected by the relay, it would open up the bypass switch and force current then to go through our control fuse, which has a quicker trip setting than our main fuse. Pretty clever scheme, and again the advantage is potentially lower cost, because now I can, with just the inclusion of this remote controlled switch, use somewhat less costly fuses. And so EasyPower makes a pretty good job of explaining this one or showing this one, and it works like this. All right, so here's our main bus. If we short the main bus normally, let's take this relay. If we didn't have this relay in the system, I'm going to deactivate it and show what our typical situation is. So typically we don't have this switch in there, so all we really are looking at is what the effects of this particular curve are for the main fault, main fuse. So you can see we have a very high incident energy on our main bus in the low voltage side of the system by virtue of the fact that this is a relatively slow acting fuse. So now if I go back and put this, what's considered a functional group in place, and the relay can operate this bypass switch, and let's go now and fault our buses. You can see while it's still 12 calories, it's dropped down by some 60% versus what it was. And so this technique can be handled both on very large systems and on areas where we have dangerous situations, whether people need to work on it or not. It may afford us some better coverage in terms of equipment protection, and it's relatively easy, cost-effective wise, and consequently that's why it's receiving a lot of positive reviews. So this is just a representative list of alternatives. As I indicated, older facilities may find options are limited, And frankly, any place you have a disconnect switch where you don't have adequate protection, adequate protective devices installed is a source for a dangerous situation, a dangerous combination of procedures maybe being out of whack due to the energies that's behind that panel, even when you've got the cover closed and you're just operating a breaker normally. So it's important, I think, in terms of protecting people and equipment that you consider what's going on procedurally and equipment capabilities. So this kind of uses our time up. I appreciate everyone attending. Certainly, as an EasyPower tool owner, you're welcome to contact tech support at easypower.com if you have questions on how to model any of these techniques, with the intent primarily of saying, okay, what if I utilize this? Does this improve my situation or not? And be able to do a risk-reward decision for your equipment or your facility specifically. We have pre-recorded several other refresher topics. You're welcome to attend and view these from online. By all means, you're welcome to look at any of the EasyPower training webinars. These are available if you go to easypower.com, support training videos, and by all means, you're welcome to download the instant online demo and or contact sales if you want to try the tools out for a more extended basis. Do want to make people aware that we have regional training classes on the website that registration is open for now. Coming up next month, we have a 5-day session in Secaucus. Then summertime, we'll have a regional training here in Portland. Later in the fall, we'll be doing training in the Vancouver area. And also look forward to an October session for harmonics and dynamic stability. Extremely valuable sessions that can help you expand your capabilities and understand how the tools could work as your needs in your local area. It's this discussion about older facilities comes to a head when you talk about harmonics and dynamic stability. Most of the buildings that were built 25, 30, 40 years ago had no concept that digital would play any part of the power distribution system. So consequently, they were not designed for anything but a 60-cycle response. But with the advent of digital controls and a lot of the power saving schemes, power control schemes that are being installed or retrofit into older systems, older facilities, there is a potential for a lot of interaction and specifically harmonics into the system, into a older facility that the original designer never anticipated. So by all means, keep that in mind, and thank you for attending this morning, and we'll talk to you next week. Have a good day. I'm going to check online to see if there's any questions, but I appreciate you very much for attending.